Now we're going to talk about one of the more trickier problems that we discuss in the second semester of general chemistry. And this is the idea of converting units of concentration. So we go from one type of concentration unit to another type of concentration unit. These calculations are so tricky because each variation is going to have subtle differences. So I'll give you an idea of some overall bulk steps that you can use to get to the right answer. But each type of calculation is going to be different. So if I go from molality to molarity or percent by weight to mole fraction, the actual steps that I need to do that conversion are going to be subtly different. So you need to have a good understanding of some basic chemistry. And the key here is when we go from one concentration to another, the amount of the solution that we have is kind of arbitrary, and we're going to take advantage of that by assuming that we have a certain amount of our solution. And in this case, what I like to do is assume that I have one of whatever the bottom unit is in my concentration. So we'll see what we mean by that here in just a second. Here in the example, I've taken solid NaOH and I've dissolved it in water to create a solution with a concentration of 1.5 molal. Now I'm asking you what's going to be the mole fraction of NaOH in that solution. Before I formally start solving the problem, what I always like to do is look at the units of that I have in the beginning, and then I look at the units of where I want to go. Here, molal is mole of solute divided by kilograms of solvent. And I want to get to mole fraction, which is mole of solute divided by mole total. You can kind of see that we're part way there in that molal gives me information about mole of solute. Well, I need mole of solute to find my mole fraction. The only other piece of information I need comes here in the fact that we need mole total to find our mole fraction. So mole total is mole of solute plus mole of solvent. We're going to find that coming up with mole solute is pretty easy. The hard part is going to be coming up with mole of solvent, but I've kind of already given you information about that by telling you that a molal is mole of solute divided by kilograms of solvent. So now really what we're going to have to do is convert kilograms of solvent into moles of solvent, and then that's going to give us all of our information. So what I like to do now that we're formally going to start trying to solve this problem is to assume that I have one of whatever my bottom unit is in my starting concentration unit. So we have a molal in the beginning, or 1.5 molal. That's like saying I have 1.5 moles of NaOH per kilogram of water. And what I'm going to do is go ahead and assume that I have 1 kilogram of water in this case. So I can arbitrarily pick how much of the solution that I have. You can do this calculation by assuming you have 1 gram or 500 grams of water, but your calculations are going to be a lot simpler if I just go ahead and use the fact that we're dealing with kilograms of water. So I assume that I have 1 kilogram of water. So if I take my unit of molality, which is molality is equal to mole of solute divided by kilograms of solvent, if I solve this for my moles of solute, it's the molality times the kilograms of my solvent is going to give me moles of my solute. So I was told that I had 1.5 molal. I assumed that I had 1 kilogram of water, and when I multiply these through, I figure out that I have 1.5 moles of NaOH in my 1 kilogram of water. So we're already halfway there, that we have the number of moles of solute. Now all we got to do is come up with the moles of the solvent. Well, we know how much water that we have because we assumed that we had 1 kilogram. And now we're going to have to apply some of the other ideas that we learned in the first semester of general chemistry. First of all, that 1 kilogram of water is equal to 1,000 grams. So that's a simple conversion. But then I need to take the fact that moles of water is equal to grams divided by molecular weight. So that's something else we saw in the first semester. Grams divided by molecular weight gives me mole. Well, I know how many grams I have, so we have 1,000 grams of water. The molecular weight of water I find by adding up that hydrogens, 1 gram per mole, or oxygens, or oxygen is 16 grams per mole. So water overall has a molecular weight of 18 grams per mole. So 1,000 grams divided by 18 grams per mole gives us the total number of moles of water inside of our 1 kilogram of water that we assume. So that's 55.6 moles. Now that we have all the pieces, we can go ahead and find our mole fraction. So part of the mole fraction, we're going to need to know what mole total is. So what's the total number of moles of solute, total moles of solvent. We found both of these pieces of information. So we found moles of NaOH, and right here we found the number of moles of water. I add those two numbers together to get the total number of moles, which is 57.1. Now that we have that information, we can go ahead and find the mole fraction. Mole fraction is equal to the moles of the solute, NaOH, divided by the total number of moles. And always remember that they use this abbreviation of a mole fraction being X. So the mole fraction of NaOH is going to be equal to this. We know how many moles of NaOH we have. We also found what the total number of moles that we have. Overall, the mole fraction in our 1.5 molal NaOH is 0.026. And I highly recommend, if you are expected to know these type of calculations, do several of the conversions, and you'll get a good rhythm going. You'll be able to understand the differences between them. And one of the things I recommend now is start with a solution that's 0.026 mole fraction of NaOH, and now convert it back into molality and see if you get your original 1.5.